I'm going to describe some of the features in our Spring Wiz program. In this case, it's a Spring Wiz Plus, has a few more features. And basically, this program is designed to help you design a valve spring pack of one, maybe two, or three springs in a spring pack. And you put in your wire diameters and such, number of active coils, and it calculates. All these yellow fields are things that are calculated from that. And then over here is the total for this particular spring. You can see for this spring specs here, it's got a spring rate of 217, 205, and 93. All added together, it's that spring rate. So anyway, you take the springs, and you have a baseline spring and a proposed spring. And you can put these either on the intake, and you saw some numbers change here, or the exhaust. And if you want, you could maybe compare two different springs on the same, let's say, intake, or you might want to compare this spring on the intake and this other spring on the exhaust. And you can see here something changed here. And you said, well, what's determining these, like the gross valve lift? And that is based on, if you click on this, cam valve train analysis, here are the cam valve train specs for the intake side and the exhaust side. And if you look over here, see weights and details, here are some weights and RPM ranges for doing the analysis. Obviously, if you've got a heavy valve train, it takes more spring to keep that under control than if you got very light components. But here are the two cam profiles, one on the intake, one on the exhaust. The one on the intake here is, you can see, determined by a cam file. If you uncheck that, then we could build a cam based on some specs up here, or if you got it set to a cam file, you click on the pick button and you can go pick like a Cam Pro Plus or a S96 profile here, some P4 format files, and pick one. Now, an interesting thing over here, when you design a cam profile, you put in, let's say, the duration at 50, the max lobe lift, some lash and rocker ratio, and that all makes perfect sense. Here's the gross valve lift, but if you've chosen one of the spec profiles here down at the bottom of the list, it opens up this new input called ramp rating. Ramp rating, I'm going to change it from 44% up to 50%. That's a more aggressive ramp. And if you see that duration at 50 or at 200 changed from, I think it was 185 to 186 something. So the more aggressive you want the profile to be, the bigger you put in for the ramp rating. You can also calculate a ramp rating based on different inputs. And let's say you know that your cam has 260 duration at 50, and it has a, let's say, a 170 degrees at 200. It will then calculate this ramp rating, which you can see is more mild than the 50% we had before. Let's say we're going to use that. Now you can see we got 170 degrees duration at 200 with that 27% ramp rating. So the point being, you can use a cam profile file, Cam Pro Plus, S96 Cam Doctor and such, many different formats, or you can build your own profile. You can also put some dwell over the nose like a cheater profile, but we're not going to do that for this. So you got two different spring packs. In this case, we're going to have one on the intake, one on the exhaust. We're going to do some analysis based on these cam profiles and these weights. And you can see, in this case, the Cam Pro Plus file has a bigger valve lift. Might be more aggressive. We don't know what the duration at 50 is and such. So, but let's do the analysis on this. Let's see what it says. Okay, here's the results. We're doing frequency analysis here. I don't know if you've heard of Don Hubbard, but he wrote a book. He worked with Harvey Crane and Crane Cams, and he wrote a book on how to do frequency analysis for a particular profile. And here's some others. This is sort of a summary of everything up here. And I'm going to take these results, and you can scroll through them. But I'm going to click on File, Display in Notepad. And it gives the same information, but it's displayed more full screen. And what have we got for our analysis here? It says, here we got the springs. Here's the natural frequency. One's being located on the intake, one's being located on the exhaust. Here's installed force, the spring rate based on all the specs. Here's bind stress. The more stress you got in your spring, the more likely it is to fail. And you can see the number 2 here, asterisk 2. If you go down here, it gives you some limits for what bind stress you should be using, what's acceptable. And you can see if it's a production engine, you better not go over 220,000 psi. If it's a race-only drag race, maybe you go up to 280,000 psi. And racing's all about pushing things to the limit. So these are definitely higher stress. One of the springs, it doesn't mean it's the main spring, but one of the springs in the pack has a stress level of well over 220,000, which means it's probably race only. You better not use this in production. And it's got a bunch of other information down here, summary of the weights that we're using, acceleration rates, the analysis RPM here. And here is the min excess force. What this is saying is, if we look over here at our graph, the required force, 809 on the intake and 746 on the exhaust, has to do with, at this point, at the peak, at the nose of the cam, here's the acceleration rate, the green, the peak acceleration rate. How much spring force is required to keep the amount of mass that we talked about, that we showed you, at 9,000 RPM? How much spring force does it keep that to stay in contact over the nose of the cam? If you don't have enough spring force, it's going to launch off the nose and probably toss up here and then probably smack down over here. And our Engine Analyzer Pro does a nice job of illustrating and going through this also. But anyway, so you can see here on the intake, for this spring that we're proposing, or on the baseline, we do not have enough force. It takes 800, and we're short by 78 pounds of force. We got a negative safety factor, which is definitely what you don't want to do. Here on the exhaust, it takes 746, probably because the exhaust valve train is a different profile, and the weights I think were a little lighter on the exhaust, which makes sense, smaller valve. And you do have over 100 pounds of excess force, more than you need. So anyway, that's some summary of what's going on here. You can see this lowest frequency RPM. This has to do with the Don Hubbard frequency analysis. And his analysis, by looking at the frequency content of this particular profile, he would say that here at 4,260 RPM, you start getting some levels of frequencies. The frequency analysis is getting above certain thresholds that he would like to see. In this case, it looks like 0.12 for a push rod, and that is 0.126, which that's higher than the limit for a push rod motor. If this was, like it says, direct acting or an overhead cam rocker arm, a stiffer valve train, this would be acceptable. But this is a push rod motor, so it's, you should probably not expose it to more than 4,200 RPM, which is obviously ridiculously low, and that's why I'm not a big fan of this frequency analysis. But it's there, and if you want to get Don Hubbard's book to read up on it, it's certainly available out there. Safety factor, etc., etc. Seating velocity, this is another important thing. When you seat, when the valve train comes back and seats right here, depending on the velocity here shown is the red, the velocity here, seating velocity. If that's high, you're going to be very hard on your valve train, especially the valve itself. And then here we got some more analysis showing that we said we're doing the analysis at 9,000 RPM. And here you can see at 9,000 RPM, we have that negative 10% safety factor, or we do not. We're short 78 pounds to hold that valve train in control for this particular profile. If you ran it at 7,000 RPM, which is well less, you have over 102 pounds of excess force. And you got a 16% safety factor. And you also have here the seating velocities, which is very, very high. You can see the limits they propose here, 30 for our drag race motor. We got seating velocities that are very high on this particular side. Could be the profile, probably is a profile, or it could be a lash setting. And over here on the exhaust, you can see we do have much more gentle seating velocities based on this limits here. And at 9,000 RPM right here, we got over 106 pounds or 14% more force than we need. So this is just a brief overview of how you can do the analysis here for a particular spring pack and hopefully pick the best spring for your particular cam and engine combination.